Hi, everybody. I have to admit, I was a little bit daunted when Dan was like 3 big ideas, so I'm going to instead tell you 3 medium-sized ideas. So this is work. I teach a class called Law, Order, and Algorithms, and I'm going to give you a 12-minute version of a semester-long course. So you get 1 extra course for free, no credit. So first big idea is that machines can be biased. And this, in some ways, I think a lot of us know this now, but if you rewind 10 years, it was something that people didn't understand. They're like, these are algorithms, they're doing math, they can't be biased, they're just, that's just not a thing that is part of a machine. So let me give you one example of this idea of machine bias. So we all carry these pretty sophisticated automated speech recognition devices in our pockets, phones. They're used to, we talk to them, they can translate, they can do all sorts of things, they can facilitate physical interactions with computers. Our worry is that they don't work equally well for all groups of the population. And so we did a very simple test a couple years ago where we took the 5 leading providers of ASR, automated speech recognition, Amazon, Apple, Google, IBM, and Microsoft, and we ran 20 hours of speech from black and white speakers through these systems, and we compared the transcripts that the machines generated to the human ground truth transcripts of what the people were actually saying. And the results were quite striking. So these are the error rates here. Lower is better, and what we're seeing is that across all 5 of these providers, we saw quite large gaps in the error rates. So black speakers were having their speech transcribed at much worse error rates than white speakers in a relative sense, about 2x, and also in an absolute sense, that when your error rates are at that blue line around 20% word error rate, many of these tools are usable. If you're down to 35, 40%, in many cases you can't interact with these systems. And so this is a qualitative difference in performance between white and black speakers in our sample. So what happened here? In some cases, in some sense, this is the easiest of the things of ways to understand machine bias. It's the easiest to fix, in that all we need to do is add more training data. So this is a case where many of the speakers that these sophisticated systems were trained on were white, and it didn't have access to the type of speech that many of the black speakers in our sample had access to. So in some sense, it's a very simple technical problem to fix, but there's also this larger organizational problem of how is it that we got to this position? What is it about the teams, the demographic composition of the teams, and of the managers and of the engineers that let us release these systems into the world in a lot of these high stakes situations. And so there are kind of 2 levels of understanding the issues, the technical level and then also the organizational level. Okay, so the second idea is that many algorithms are deeply problematic in the ways that I just explained, but in many cases they can also be used to combat bias in human decisions. And so I'm gonna switch to the criminal legal system and tell you a little bit about charging decisions. And so after somebody is arrested in the United States, prosecutors have to make this high stakes decision about whether or not to charge that individual for an offense. And in many cases, this is largely based on narratives that officers write at the time of the incident. So there's a worry that these narratives contain all sorts of racial cues, sometimes explicit mentions of race, and they can kind of prompt implicit or even explicit bias in the decisions that prosecutors make. So we developed this natural language processing tool that automatically masks race-related information from these police narratives. So when prosecutors are deciding whom to charge, they're looking at these redacted narratives, and then hopefully some of this bias is not present in their decisions. And so how does this work? Let me give you a toy example. And so here, this is a stylized version of what prosecutors are seeing when they're making these decisions. And so there are explicit mentions of race here. We redact it to just say, instead of black, we say race. But we don't want to redact things that don't refer to race, like black jacket. We see brown hair, again, a physical description, not really relevant for the charging decision, but it gives us some clue about the racial identity of the people involved, and so we redact that. Names, again, in many cases are indicative of someone's race or ethnicity. We redact those. The location, because of segregation in a lot of American cities, we know if we know the location, we also have a guess of who's involved. Again, we redact that. It doesn't really tell us much useful information that a prosecutor needs when they're making these charging decisions. And we've even heard that in many instances, prosecutors know the officers, they know where they're stationed, which neighborhoods they patrol, and so if they know the officer's name, they can infer the location, and from the location, they can infer the race of the people involved. So we also redact that. And so this is how our race redaction works. This recently inspired a law in California that mandates the use of blind charging across the state by 2025. So one thing about this example, which I think is particularly salient, is that it highlights some of the technical or some of the limits of technological solutions to policy problems. And so in this case, it's making it difficult to act with animus when making these types of charging decisions where we're redacting this racial information, but at the same time, it doesn't do anything about unjust laws that might have disproportionate racial burdens. And so think drug laws or other types of laws that even if they are applied in a completely race-blind, race-neutral manner, they still would have disproportionate impacts, in many ways unjust impacts, on communities of color. And so it highlights what I'm calling the difference between disparate treatment, explicit uses of race to make decisions versus disparate impact. Even if our decisions are facially neutral or race blind, they could still have impacts on communities of color. So there's a limit between these what this algorithm can ultimately address. So finally, I want to talk about the ways that we need to align algorithms to ensure that they're carrying out policies that we ultimately want to promote. And so I, again, want to stay in the criminal legal system and tell you a slightly different example. So in many jurisdictions, people can be jailed for failing to appear at mandatory court dates. And as a result, it's possible to reduce this type of incarceration by helping people make it to court. So one way to help people make it to court is to provide free door-to-door rideshare service from their home to their court. So we talked to a lot of people, and we've heard all sorts of understandable, justifiable reasons that people are missing court. Usually they don't miss court because they're trying to actively flee or skirt the law. Really, they're for reasons like lack of transportation, lack of childcare, inability to take time off of work. Now, of course, it would be better to just not jail people for missing court. We don't revoke someone's health insurance if they miss a doctor's appointment. We understand that there's a cost to the system, but that's a pretty harsh consequence. But the way the legal system works is that if you miss one of these mandatory court dates, often you will be arrested. A bench warrant will be issued for your arrest. Next time you interact with law enforcement, you'll be arrested. And so we want to reduce this arrest by trying to help people make it to court. So we've been experimenting with this in California, and we have a budget. So we're working with a public defender in California, and there's a fixed budget for how much we can spend to help people get from their home to court and back. And the budget isn't big enough to give everybody a ride. And so this question arises of who should we give the rides to? Ideally, we would like to give this assistance to everybody. In many problems, and in this point in particular, we don't have all the resources to do that. That's like a standard policy trade-off that we have, that we just don't have. We have limited resources to provide the benefit. And so who should we give the rides to? So this is a difficult problem. One way to think about this problem is that the way I set it up at the beginning is I want to get the most people to court. I want to maximally reduce the number of people who are incarcerated for missing court if I want to get the most people to court. Okay, so now let's play out that strategy and see what happens. And so here's Boston. It's coded by demographic, and so we see the demographic makeup of Boston, and like many American cities, it's pretty segregated. And the star there is the main courthouse. So now if we take the strategy of trying to get the most people to court, given our limited budget, who are we going to give the rides to? We're mostly going to give the rides to people who are relatively close to the court. Why is that? Because they're the cheapest to give the rides to. Okay, and so it costs a lot more to give rides to people who are on the outskirts. And so given that we have a fixed budget, we want to get the most people to court, we want to reduce the amount of incarceration for missing court the most, we're mostly going to give rides to people who are close to the court. In Boston, this is mostly white folks. Okay, so this is one of the, we started off with a very reasonable objective: minimize incarceration, maximize the number of people to court. And who do we ultimately give the rides to? We give it to people who are generally white in Boston. Okay, and maybe that's okay, but many people think this is problematic. And so there's an alternative way that we can think about this allocation problem of saying, well, let's give rides equally to people across neighborhoods in the city. Okay, so we might say, well, the same proportion of people in the outskirts of the city get rides as the proportion of people who are close to the courthouse. And if we do this, again, let's play out these two different scenarios that I've described. So the first scenario, where we're not going to put any restrictions, and we're going to say maximize the number of people who make it to court, minimize incarceration. With our budget, let's say that we get 1,000 extra people to court. 1,000 fewer people are incarcerated for missing court, but in the scenario, 30% of one group gets rides, and 10% of the other group gets rides. Right, and here we're thinking mostly white individuals are getting rides, and non-white folks, racial minorities, are getting rides at these lower rates. Okay, so alternatively, we can think about equal allocation, where now 20% of both of these groups, the white folks and racial minorities, are getting rides, but at the same time, because we've put this constraint that we have equal allocation across groups, that means we're going to end up giving rides to people for whom it's not efficient, quote unquote efficient, to give them rides. That means we're going to, if they live farther out, we're going to run out of money faster. That means we're going to not be able to give as many people rides. Fewer people are going to make it to court, and more people are going to be incarcerated. And in this hypothetical, that means 800 extra people will make it to court. That means 200 extra people will be incarcerated relative to giving everybody a ride kind of in this efficient, quote unquote, efficient manner. Okay, so this is an implicit trade-off. Again, in many scenarios, many situations, it's impossible to break free from. It's just a trade-off that's inherent to the problem. So now, I want to ask you all to think about this trade-off, and we can switch the, and so you're going to see this. I'm going to ask you to vote in a minute, and there's a spectrum for maximizing appearances on the left to equal allocation on the right, and we're going to see a code in a minute to put your response. You can scan this code, and again, all of these. The thing to remember, so it's a very hard choice when you're trying to decide what to do here. It's a very hard choice. All of these individuals, or in this case, in my scenario, they're public defender clients. They all have need. They're all kind of tied up in the criminal legal system. And so now we have to make these hard choices about how do we want to allocate this limited resource. I don't think there's any easy answer here, but I'd like you to try to answer the question. So more on the maximizing it the most people to court, minimize incarceration, versus getting equal allocation across groups, but that means more incarceration. So where do we fall on the spectrum? We'll just give you another couple seconds while to think about this hard question. You only get 10 seconds to make this choice. Okay, let's see it. Yeah, you want to reveal do the responses. Okay. So this is what always happens. We've run representative surveys across the country, and it shows the challenge of this problem. So we can design an algorithm to fall anywhere on the spectrum. That's a technically feasible thing to do, but we still have this problem of democratic governance, of deciding what exactly is it that we want to achieve. And so this is the third big idea, that we have to figure out what we want to align our shared ideals with the algorithms that we deploy. And if we don't do that, then we're going to be implicitly making these choices embedded in the code itself. Okay, so just wrapping up. First idea, a lot of algorithms can exhibit troubling disparities, like automated speech recognition. Even though many algorithms are biased in these serious ways, they can still be used to mitigate the biases of human decision makers, like our blind charging algorithm. And then finally, algorithms encode policy, and we must grapple with these inherent trade-offs that are implicit and inherent to all these policy choices. Thanks, everybody.